Right, so welcome to part 2 of linear regression. So we already went through a whole, I think we went through a whole lot from last time. And I think, hopefully we have a decent idea, at least what linear regression is and what it can do. We're going to continue that conversation. As I mentioned before, I started the recording or people kind of filed in. What's it called? The topics 18 and 19, I kind of combine them together when we talk about them. So just kind of be aware that like you might see some of the stuff we talked about today also in section 18, and then we'll probably talk about some stuff that's in 19, which is multiple linear regression. All right. So let me share my screen. Oh, where did my window go? Oh, I was missing my window. I'm like, oh no, but that's good. Let's see here. Let me share my screen. And just kind of reviewing while I kind of pull up my screen. We talked a lot about machine learning, we introduced the idea of linear regression, and then we started talking about multiple linear regression. And I believe I showed you all a snippet from this notebook here, which again, was like a notebook in progress, where we kind of went through a little bit of using this wine data set and kind of looking at how we can use Sklearn to perform a linear regression. And again, like scikit-learn, Sklearn, technically scikit-learn, but that will be a very common package we'll use in other machine learning algorithms and stuff. So that's kind of a good thing to just kind of know and like how to use. One thing I did not show last time, which I want to show now, is using stats models, which is another Python package, which is actually based around a package in R, which is why the output and like using it's a little funky, or at least a little different from like your normal Python factors and stuff like that. So let me go ahead and we're going to kind of scrolling through here. I'm going to make sure I actually run everything I'm supposed to. And we're going to skip all the way down to the wine data set, run all this stuff. So last time we saw how we could load the wine data frame. So we have this data of fixed acidity, all these different features. And then finally, I think it's a little off to the side here. Oops, wrong side. Is this quality attribute. That's kind of our target. That's what we're kind of looking to predict. And then, so, we could do some exploration, but we're going to skip over that. And then we're just going to go straight into performing the regression. So we saw that we would basically make sure we have our prediction, our features, and then our target separate from each other. And let's see here. One thing we'll have to do that's different from scikit-learn than it is from OLS stats models. Note that I imported stats models here with SM, so just kind of hopping up to the top real quick. There we go. Is that we import, where is it, stats models, the stats models.api as SM. So that's just a little bit easier for us to type out. It's a pretty common way to phrase it. So I lost my place now. I think we're right here. There we go. So one thing we have to do that's different, we have our predictions and our wine target. We have to actually add this constant here. And the reason why, it's just basically this is telling stats models that when you make the prediction that we actually are using, we have a y-intercept essentially. So by default, it doesn't include one. So if you look here, if I run this predictors, make sure I have this right. There we go. You'll see that there should be a constant. There's a constant. You can see it's just adding that one in there. And basically just showing, oh, there's some kind of y-intercept. So that's a little bit different that we have to add in there. Once we have that though, we can actually run the model. It's kind of similar to scikit-learn with a dot fit. And we have our target, our predictors, note that's sm.ols.fit. And then we actually have this model, and the model's trained now. So to actually check out the what came out of that model, we do model.summary. And this is where we get this large output of information. So real quick, did we actually see any of this, like this little output here? Give me a thumbs up if we have. Okay, I know we talked about into alpha hour, so I wasn't sure if we talked about it in the main lecture, study group at the time. So you can see here is that we talked about the R-squared value. We saw before it was 0.297. Note that I did mention this R-squared, sometimes also called coefficient of determination. So just know that those are two of the same thing. And we have adjusted R squared, which I didn't really mention, I think, last time, but you should know that adjusted R squared basically factors in the fact that if we have many, many features, we might by chance just do a better job of making a prediction, but it doesn't necessarily mean that like that feature should be included. So adjusted R squared basically scales down R squared to depending on how many features you have. So if you have more features, your adjusted R squared will actually get smaller than R squared. In this case, because I have a decent amount, it's not too much lower, 0.295. Okay. Now this is a whole bunch of stuff coming out here. I didn't mention all of this stuff, and I'm not going to talk about every single part. You can see there's a whole bunch of information, but the main things I want to point out is the R squared, adjusted R squared, and then the F statistic, well, really the probability of the F statistic. So if you recall, like F statistic was back from ANOVA, right? So that's really what that's coming from, is that this is actually, in a sense, doing an ANOVA test. And what you can kind of think of this as is basically saying, what's the probability that this model is actually predicting the data, or doing, making a real prediction on the data. And so basically these values are significant. And the smaller the p-value, basically, usually we say like 0.05, right, for our alpha. If it's smaller than that, basically you can say, yeah, we're making a model that actually like does some prediction. It's not just completely random guesses. So that's a good thing. That's a pretty quick thing that you'd want to check. Okay. And you can also see some extra stuff like observations, not typical things we really care about. Now, here we see on the kind of feature, this is the feature list. So this is kind of nice with LS, like, actually printing out these things, is that in scikit-learn, we basically just get the coefficients. But here we actually see all the values, or not the values, the features themselves, since we fed it in through a data frame. So they're all named, which actually makes it really convenient to actually see what this coefficient refers to. Note that we did not scale this time, which is why we're seeing this huge value. So if you remember back to when we talked about scaling, that just helps with interpretation, but we can still read this off. Now, there's some new information that we probably haven't really looked at when we talked about scikit-learn. Usually we just get the coefficient and R squared, with the score, and that's kind of it. So with this on the right here, with the standard error, really I'm going to focus on t value and the p greater than or equal, or greater than the absolute value of t. These guys are our t statistic and our p value. And if you remember, that's really from a hypothesis test, right? And what this is basically trying to tell us is like, hey, like this value of the coefficient, this is what we found that was the coefficient, the value, I should say, like how much strength or how much we should kind of scale up this feature to make a prediction. This t statistic and then really this p value here is telling us, saying, is it significant? Is it like, sure, we can put a number in there, but is it actually significant? And what you'll see here is that there's actually, most of them are pretty small, which is a good, like, it's a good, like, it's a good thing. It's like, oh, good, these features actually do matter in the overall prediction. But there are a couple on here that start getting a little bit higher. And this one, you're like, oh, 0.024, but that's still pretty low. So it's pretty certain that this is at least an actual factor. But we can see here in citric acid, right here, the p-value is 0.43, which you think about that, that's pretty high, right? That's definitely not significant. And what this is basically saying is that citric acid, even though we have a coefficient for it, it's not really, it's likely not a real predictor for the target. So basically this is saying like, hey, this feature right here is not really needed. You don't need this feature to make any predictions. It's not helping. So in that case, you actually might want to drop citric acid and then rerun the model. And the coefficients will slightly adjust, depending on what this citric acid is like what citric acid actually did to the model for prediction. And the reason why you would actually drop this is because then our adjusted R squared would actually likely, well, maybe not go up, but this would be more realistic because we're using less features. So in a lot of ways, we want to use the least number of features as possible to make a prediction. And hopefully that makes sense too. If you have so many different features, there's a chance that like some of those features just don't have any real effect and you're just using that in your model that doesn't really make sense. So the fewer features you have, kind of like the more like you're like certain, like not certain, but like more confident that you're like, yes, each of these features are important to making that prediction. Okay. For the record though, if you do drop out certain features, even if they are insignificant, or at least, according to the p-value, you still might see your R squared value and even your adjusted R squared value drop. And that's because basically there's just less predictive power in there. So there's actually a lot of debate about whether you should use R squared to really determine how well your model does. but it's a pretty typical one, and you just have to kind of know a little bit of the context. The biggest thing is just understanding where your model is and whether it makes sense. For example, maybe I'm not a wine person, but maybe something about citric acid, like there's not really a thing about quality in there, or maybe that, maybe there's equal number of people who, some people really like citric acid, some people really hate citric acid in their wine. And so it kind of balances out, there might be something like that in there. So those are kind of things that you would ask for domain knowledge, whether you would research and investigate yourself or talk to someone else who does have that knowledge in, whatever you're looking at. Okay, cool. Does that make sense, people? Yeah. Any questions?
Yeah, quick question. Were you just saying to drop citric acid just as an example, or is there a value in there that you were looking at?
Oh, yes. Yeah, I was looking at this specific value to say, oh, I think I should drop citric acid because this is essentially representing the p-value. This guy right here saying, hey, this is a pretty high p-value, 0.43. Usually we're looking at 0.05 and lower. So this seems likely that this model is saying like, hey, this feature, I'm incorporating it into my model to predict the target, but this might not actually be significant. And
okay, yeah.
Yeah, does that clear things up, Eric?
Yeah, sorry, I might have just cut out for a second.
Okay.
I missed that.
And then, I think I'm struck by, you have what, 12 significant variables there that have p-values of 0 essentially, but we're only explaining about 30% of the variation through the R-squared. So that's where there's other factors outside of our model. We just happen to be lucky to have so many that are significant.
That's right. Yeah, you can think of it like we have this many features, maybe take off citric acid, but the rest of these features are at least significant enough to should be included in the model. But like you said, we only have about like 0.3, or we kind of like 30% of the variance is explained with these features, which means basically there's more complexity in making predictions, which could be that there's features that we need to go out and collect. So like we need to go do more research on these data points, and maybe there's some other factors. I think I mentioned last time, like maybe like what bottle it's put in, or something like that might be an actual factor for quality in this case. So that's something that we're not measuring at all. There's also certain things that maybe what we call interacting features. So this is actually something we might talk about today, is that, for example, maybe if something's like has a really high residual sugar, I think in this case it actually goes up. So like a high residual sugar has higher quality, but maybe if you have high residual sugar and let's say a high fixed acidity, you actually drop in quality. So maybe those two together are like, oh, that's not as ideal for quality, at least for the quality. And so we'd actually ideally want something that interacts these two together. Another one you can think of is maybe there's some kind of like parabolic or quadratic or some kind of polynomial relationship. So the idea there is maybe, here this model's assuming that as we increase residual sugar, we increase the quality, by a certain amount. But maybe it only happens to a certain degree and then it starts dropping, lower and lower and lower. So you have something more quadratic, or even something even more complicated than that. In that case, you would need to add more complexity into there. And essentially what that means is just adding more features into this model. Okay. Cool. Yeah, all great questions. Anything else?
Just one quick question. Like, what is the constant coefficient? Like, what is that referring to?
Yeah, so this is kind of, you can think of like the y-intercept. Of course, this is like, multi-dimensional. This is basically like, this is where like, I didn't scale the features. Like we did standard scaling last time. So last time when we did standard scaling, this actually represented just like the average value for the target. You can kind of think of this as an initial point. Of course, in this situation, since we didn't scale anything, this is basically just a starting off point. So setting everything to 0, you would expect the quality to be 104, which probably doesn't make much sense in this, instance, because making all of these 0 and then having the constant, for example, say, oh, set all these to 0, now we have a quality of 104, where the quality, I think, went as high as like 9. Probably doesn't make much sense. So it's hard to interpret this, but you can think of it as a system value that doesn't change depending on the features. Cool. Yeah. So anyway, this is our output here. This is again using OLS. You can, for the record, like build up all of this information using the scikit-learn model but you got to do it by hand. Essentially, you have to basically make sure you do all of these parts in here if you wanted to get these values. For example, you could do the p-value for this too, but it means you have to take some extra time to actually build up those functions and stuff. So I will say, there's quite an advantage in using these, using OLS, which will produce this table for linear regression. But the reason why people tend to use scikit-learn, even for linear regression, even though it's not doesn't produce as much, it's actually really easy to change out what kind of model you use with scikit-learn. So that's part of the reason why people use it quite a lot. And that's actually the real reason why I use it a lot, is because I'll use the linear regression to get an idea of like how well can I perform on this data, and then it's like, okay, can I use a different model to do even better on this prediction? Okay, sound pretty good? Okay, cool. All right, so I think I'm going to come back to, maybe we'll come back to this notebook. I'm actually going to go back to just one of our notebooks here, multiple linear regression. So this is a new one that we haven't talked about, and we're going to talk about a few things about, in a sense, like when we, especially when we talk about multiple linear regression, there's a lot of these extra ways we can tweak our features. So just going through, we're going to import our normal libraries and everything like that. And again, instead of using one feature, we're going to use multiple features. So I'm going to go through some example code here, and just know that most of this right here is just basically creating just some like random data. So note that there's nothing special about this data by itself. And we can just quickly look what this data looks like. So again, this is not real data. I just kind of generated it right here, right? And you can see here is that we have, in this case, I'm just defining it as seniority and then maybe like monthly income. So in general, as seniority increases, monthly income increases. Pretty straightforward. And you can see here, in this case, I actually write a little line through this, which is probably about what the linear regression line would look like for the simple linear regression. Okay, kind of emphasizing, like, you know, like this is where, like, talk about multiple linear regression. Like there's 3 variables, you'd have a not hyperplane, but like 3D plane, or actually 2D plane and a 3D coordinate system. So we kind of talked about that. I like to think of it more like dials versus like this, though this is the classic mathematical interpretation of multiple linear regression. Okay, so this takes us to categorical variables. So this is actually similar if you guys have gone through section topic 18. I think this actually comes from that topic. So right here we have some data. We have, you know, it looks like about cars, miles per gallon, cylinders, displacement, horsepower, weight, acceleration, model year, origin, and car name. So we can probably look this up and probably kind of get some you know, reasonable guesses what this is. Cylinders is probably the number of cylinders, so like an 8-cylinder car. Displacement, I'd have to look at like what exactly that is, but it turns out to be related to the engine, I believe, at least for this data set. And then we also have like the model year, which probably is 1970, since 2070 hasn't happened yet. And I think 1870 might be a little too old for us to consider looking at those cars. So that's kind of some context there. Origin, it turns out, is actually the origin of where the car was manufactured. So we can kind of check that out. You know, we could explore it, look at the data to make sure we understand the context. But this is the data we have. And of course, we have the car name. Okay. So the thing about this is that you look at this, you're like, we have some values that we kind of saw like in the wine data set. Most of those, except for the wine or red wine, were numerical values. So like you can imagine like adjusting it, you know, along the spectrum. Some of these values, though, I would argue don't really make sense in a continuous way, that we would adjust the value over like, you know, some, when I say continuous, like, you know, things like discrete. So like, for example, number of cylinders, I could be wrong, but I don't think there's really an idea of a 2.5 cylinder. So I think in this sense, like we have more discrete values. One obvious category is origin. And we'll see actually if I do, let's see here, this is data. If I do data dot, let's see here, let's do describe. You can see some values here. For example, looks like the max value is 3, 2, 1, and it's probably in this case an integer value. And we could double check that, but you could probably see that this would be an integer value. And since I know the origin, actually this number corresponds to where it was manufactured, it makes more sense to think that this is going to be some kind of category. Okay, so the thing is, like, how do we deal with those categories? Like, we could try to keep them as numbers, right? But what could be some issues if we did try to keep them as numbers? You might have an idea. Yeah. Think about, I'll say specifically origin. Like, let's say 1 corresponds to North America, 2 is Europe, and 3 is like Asia. Okay, what would be some issues with having those as numbers like that? And then using inner model.
Well, you'd be saying something like, Europe is more valuable than US.
Yeah, there's some kind of inherent like structure here saying US is 1, Europe is 2, and Asia is 3. And you're like, but we could have easily, like in this case, we could say, well, why couldn't Europe be 1, and 2? Like, what makes those really different? And in a lot of cases, I think that's where like you can kind of think of like if you had like, let's say car color wasn't this one of the features, putting red as 1, green as 2 doesn't really make as much sense, because it's not like red is not twice as good as, or green is not twice as good as red. In the same way here, like Chuck had said, is like, let's say 2 is Europe. Is Europe twice as good as America? And in what context does that actually mean? It's not super obvious. And I'd probably say like, it's more of a categorical, like we could call it ABC. It would have been the same kind of proxy. So that's a big thing of like realizing it's categorical. There's a few methods you can do. So this is probably something when people are doing their linear regression, when students do this, I think this is usually the question that everyone comes up with, like, when is it a category versus not a category? Because maybe you could argue a whole lot of things. Like one could be that maybe cylinders should be a category, maybe it should actually be numerical. Maybe, and so I've seen people argue, maybe miles per gallon should actually be a category as well. Like maybe that makes more sense than versus like a continuum for this data set. I don't know. So first thing we can do is actually like explore the data. So data.info is really helpful to first just kind of identify, when we have integers versus floats. And those are usually a pretty big, like suggestion of like whether it should be category or not. One example, you might have an object. In this case, we're probably not going to use the car name as one of the categories, but you could imagine like we had something like red, blue, green. That would probably be a category in that case, and that would be labeled as object. Note that I kind of mentioned cylinders here, and it is an integer, but if for some reason like there's a typo or someone put 8.0, it could be read as a float 64, which doesn't necessarily immediately tell you it's not a category or not. So this is just kind of like a hint to like what could be. Okay, and of course we got data.describe, and what that does, we can kind of look at a little bit of the spread of the data, for example, the minimum, the maximum, and these different quartiles. So this kind of gives you an idea of like what these values kind of hang around and stuff like that. Okay, that's kind of like the first very initial spot. Okay, the next thing is probably like what I would say probably what you'd end up wanting to do would be actually plotting out these values. And I think this actually in the lab does something very similar to this, where essentially you plot out saying, okay, let me plot the cylinders by, in this case, let's pretend we're trying to predict MPG, miles per gallon, right? So we kind of do our feature versus our target. And you can see here is that we have cylinders kind of being this very specific point. And that makes sense for discrete values. And what we're trying to capture here is that, does it make sense to group these together as a category that's not having a specific pattern? So here you might say like, okay, like cylinders, it looks like, we have a big grouping here, and then a big grouping here, and a big grouping here. And I might argue, it's like, that does look like as we increase the number of cylinders, we do decrease in miles per gallon. So maybe it does make more sense to keep that as a continuous variable. You can also argue saying, there's really only, 1, 2, 3 categories here. And maybe that makes more sense to keep those as those categories. Honestly, at this level, I think it could go either way. Model year, you can see here, we definitely have discrete values, and there does seem to be a general trend upwards. So here, again, it's one of those things where like, it could go either way. Like you could maybe say like, as the year increases, like as we increase the year, we actually, have some trend towards miles per gallon. But you can also see that there's some values here, like for example, it looks like maybe 73, 74. We kind of have these different kind of like bimodal distributions here. And you can kind of see like this clustering. You guys see that little kind of like a little more heavier like dots on certain areas. That's just showing us like where the data is clustered. So in this case, like, what, there does seem to be a general trend, but I don't know if I could like, like maybe this kind of like, it's not every single car in this value. So maybe it makes more sense then to actually keep these as a category and just know that like a 1975 car is less of fuel efficient than like a 1980s car, you know, and that might be something that would be factored in. Another thing you can also do is maybe kind of capture these together as like, you know, let's say the 70s car, you know, it's like, oh, 1970s car, and making that as one category. And so actually transforming these values for model year instead of 71, 72, 73, maybe it makes more sense to capture them together. Say, oh, this is all the 70s, you know, and then this is all the 80s. And that might be a little bit, might help a little bit more because it's kind of getting rid of some of this extra complexity in there. So, but not every case makes sense each time. Okay, does that make sense to people? Everyone follow me? Okay, cool. Again, feel free to interrupt me if something sounds off or you have a question. Origin here. Origin is probably the biggest candidate for category, like a category, because we know in the context here, like I kind of just made it up, but it's something along the lines of like North America, Europe, and Asia. Even though there does seem to be a general trend kind of going upwards as we go from 1 to 3, it does, the fact that there's only 3 different values really kind of suggests like we should maybe treat this as a category, because we also see there's a huge spread in where these values are in miles per gallon. So that's a pretty good suggestion, is that maybe, you know, a car in this origin, it depends on some other features too, why it ends up in this distribution. Okay, so that all makes sense to everyone? Cool. All right. So one way you can do this too, like I showed like 3 specific, you know, features. Now I'll give you a warning. It's like, if you have many, many features, don't do this, because your computer will kind of like freeze up a little bit and then you won't be able to read it anyway. But you can do something with Seaborn called pair plots. And I'm just feeding the data here. And what this will do basically will generate multiple graphs of each feature versus the other feature. So there we go. And so there's a lot going on in here, but basically, and I know the text is a little small for everyone, but just kind of know that each on here is like miles per gallon, cylinders, displacement. And then on the bottom here is like each of the features, miles per gallon, cylinders, displacement, and so on. And so what you can kind of think of it is that, like, for example, this little graph right here is weight by mile per gallon. And what we're trying to look for is essentially patterns. So you can first of all see, like, you know, let's say that mile per gallon is really our feature, that our target that we really care about. You might look at just mainly this line right here, and you can kind of see is that we see cylinders. Sorry, I have to kind of scroll down a little bit to see it. Cylinders displacement, or sorry, cylinders right here. We definitely have these categories like we saw up there, but the rest of these ones more or less kind of flow. And we even see, like, if you look carefully, it looks kind of not quite linear, maybe a little more quadratic, or not quadratic, but kind of like a decaying exponential. So you can kind of see a little bit of an idea of where these values kind of fit and how they relate to each other. Sometimes it's also important, you can kind of look, for example, I talked about origin, is that there might be sometimes clusters on other categories. So in this case, like you can see is that origin, it looks like origins 2 and 3 displacement is pretty much just right here, but on origin 1, there definitely seems to be more spread out value. So that's something that you can kind of like look into it. So there's some really cool stuff you can kind of find in here and see, like, if there's any relationships. Now, the one thing that you probably might notice is that, what about this diagonal here? Because it's very different from the rest of it. And that's because we have miles per gallon here versus mile per gallon here. And if I had mile per gallon here and mile per gallon here and actually plotted out those values, what would I expect to see? And I'll give you a hint, it's not this.
It would just be a straight line.
Yeah, it'd be a straight line that just kind of keeps increasing, right? And that would be true for not just miles per gallon, but for all of them. Is to basically just be a straight line going up. And so since the pair plot's like, hey, this is probably not super useful, like just having a straight line for every single one, this basically just showing the distribution for each of these features. So you can see here is basically saying, okay, how many are in this case for cylinders? Most of them are, it looks like, you know, cylinder 4, there's some cylinder 8, and I think this was cylinder 6. So you can see here is a little bit of distribution. You see a couple, you know, 5, and I think this was like 3. And you can kind of get the same idea down here. So this can be really useful. So this one I want to kind of, I think some of these are kind of interesting, but this one in particular is really interesting to me. So this one's model year by model year. What do you notice about this? And can someone tell me, like, maybe what explains these? huge spikes.
Well, I mean, cars go through like major overhauls like every 5 years.
Mhm.
So every 5th model year, they have like a complete overhaul of their like platform. So that could be a big spike in people waiting to buy,
Yeah.
in those years.
Yeah, so one thing could be just like the fact that we know that, the model years, there's a new revamped model about every 5 years, that maybe people are actually buying more of these cars. So we actually see this spike in here. There's also another explanation that could maybe explain why we see 1970, 1975, and 1980 cars so predominantly in this plot. Anyone got a guess?
Maybe they just don't have the exact number, so they're estimating.
Yeah, so that's also a possibility too, is that maybe, for example, this data has been collected over time, and a 1972 car, they're like, well, that's 1970, so they put 70 on here. So that's something to keep in mind too, is to know that this data, what does this actually correspond to? I think trucks make sense, from the domain, but you'd have to double check and say, is this actually a pattern in there, or is it something about the labeling of the data? And this is a more subtle issue where you have to know how the data was collected and labeled and all that stuff. Okay. Cool. Any other questions about what we're seeing here, or how we can use this?
Yeah, I have one quick question. So if you look at the horsepower, the weight, and the displacement, they seem to have very, especially in that first column, they seem to be very similar.
Sorry, so this
In the first, in the miles, their relationship with the miles per gallon,
Mhm.
like the displacement, horsepower, and weight, they all kind of look like bananas.
Yes. Okay. I'm sorry. I said you said displacement. I realized I'm looking at the wrong one. Yeah, you're right. There's kind of like this general kind of trend downwards, which could be interesting. Yeah. So you're just saying like something you noticed.
Something I noticed, and then just kind of how we kind of look at them as being independent, but it does seem like they're not.
Mm-hmm. Yeah, and that's a good point, is that we do assume like displacement, horsepower, in this case weight, to be independent variables. But you can probably guess is that like this probably is coming similar to like the engine in general. It's probably describing the engine together. And this is where we get multicollinearity, where basically we have multiple features describing very similar things. And you can kind of think of it as like there's no feature in here that's like, engine overall, which would describe all of these three together. You can kind of think as each of these features are saying something probably about the engine, but maybe have slightly different views on it. The way I kind of like to explain this is like, I don't know if anyone knows this story, but like there's a story of like having, it's like a parable or whatever, of this elephant, and a group of blind men come over and they feel the elephant, and one person feels the tail, one person feels the ear, one person feels the trunk, and they each conclude something different based on what they were, what part of the elephant they were feeling. It's like, oh, this tail, it's like, oh, it's clearly a broom, but it's actually an elephant's tail. That's kind of like, you can kind of think of this viewpoint too, is that maybe it's explaining a little bit different stuff, but overall maybe talking about the engine. Yeah, it's fine.
So,
yes.
So in this plot, like, can we I think we usually ignore those vertical and horizontal plots because they are not really intuitive about the relationship, right? Can we assume like that?
You're saying like for the regression, ignore these.
No. Yeah. So the plot that has that vertical line or the horizontal lines, because they.
Mm-hmm.
Yeah. For example, the second plot, does that tell any relationship? And I don't really get any intuition from that plot, that cross plot,
Yeah. So you're talking about this cell right here by my cursor, right? Like, or something like
yeah,
this.
yeah, something like that, or something that is horizontal, like opposite of that, right? So
right. Yeah. So in this case, let's go back to like it being miles per gallon. right here, and this is going to be, let's say, cylinders, right? You can kind of say is that like we see that there's more variation in like this case. It's like I think a cylinder 4. So there's more variation in here, and there's less variation on I think it was 6 and 8 cylinders. So the thing about that is like that does tell us some information, and this might tell us a little bit is that it looks like a 4-cylinder engine tends to have a higher mile per gallon than an 8-cylinder engine. And so there is some pattern in there. It's just not as easily like, you know, there's no continuum where it's like, what if I changed it to like 2.5 or 2.3 and whatnot. So you can still actually get some information from here, and we'll actually use this. You can use this in a linear regression too. And what the way I kind of explain it is, this is kind of a good suggestion for categorical. It's kind of like saying, if it's a 4-cylinder engine, there might be a general trend upward. So you might boost up the 4-cylinder cars, the target a little bit higher, or you know, a little bit lower, depending on what category it is. So it's kind of like it changes its baseline, if that makes sense. That's the way I kind of view the categorical values. And in fact, mathematically speaking, they're very similar to basically just adding a new constant depending on what category it is. Okay, so does that kind of make sense, Simon?
Yeah, I was just trying to like how to extract what kind of relationship is that we can extract from such figures, you know, like.
Yeah, it is a little tougher, I think. I think it's a little bit easier to look at this more continuous.
Yeah, exactly. Yeah.
Yeah, and there is some information there. It's just a little bit harder to like get out, and that's where, you know, we get this to just like, okay, like this might make more sense as a category. Let's see here. I wanted to see what this was. I can't remember what I was plotting here. I think I was just showing a little bit of distribution, so that's okay. Okay, so all right, let's say we identify something like the cylinder's origin to be category. You know, how do we do this? There's a couple ways we can do this. One is called label encoding, which I'll say up front is like, I don't think is usually the best option. Usually we'll talk about dummy variables, one-hot encoding, but I'll show you what this label encoding does. So let's say we have cylinders, for example, and instead of having, you know, it's like we have a 4-cylinder car, a 6-cylinder car, an 8-cylinder car, maybe it makes more sense to really call it like category 1, category 2, category 3. And that way we kind of keep it separated from like this number. This number might be more confusing than it actually is. So that's where the idea of like label encoding comes in. So what we can do now is we can actually change this feature by doing data, the feature, right? And then just changing the type as category. So now if I actually check out, let's see, data, let's do info. We should actually see category. It actually changes to category. So basically Pandas now knows that this data frame is like, oh, this is not just like an integer number. This is actually a category feature, which allows you to kind of play with a little bit, makes it a little bit easier to play around with. So one thing you can do, for example, is check out the unique, which we normally could do with integers, but you can see also we can do the same thing with it being categories. We can see that there's 5 categories, and they are, in this case, just in 64s, but it's kind of nice to be able to have this output. And then what we can also do is to actually produce the category codes. So this basically relabels the different categories. So there's 5 different categories, which basically makes go from 0, if I remember this right, it should be 0, 1, 2, 3, 4 as the labels for those. So this ends up being like, you know, category 1, category 2, category 3, category 4. And so it kind of abstracts away the fact that these are like 8, 4, 6. These are especially useful when you're looking more in the sense of like, let's say something like color, which doesn't really have, like in most cases, a lot of numerical value. So we can actually use these categorical codes to kind of abstract that away and say, okay, this is category 1. But sometimes you might have something like this, where you have an 8-cylinder car, a 4-cylinder car, a 6-cylinder car. It's that it might make more sense to kind of get rid of that number because it doesn't really make sense in the context of what we're looking at. So it's just a way to kind of get this encoding. You can also do this with scikit-learn. So sklearn preprocessing label encoder. So this label encoder basically allows us to do the same exact thing, but does it with the sklearn API. So basically, like we saw last time with like fitting, or start scaling the data, we'd have this label encoder, and this basically allows us this encoder. We do a dot fit, and note that this dot fit transform basically does 2 things. We could have done dot fit and then do dot transform, but we're just doing it all at once. So we do a dot fit transform, and this is transforming, in this case, the data origin. So basically the dot fit part looks at the data origin, the series, and says, how many categories are there? And then the transform part actually transforms those categories into, identifying those different category numbers and actually transform the data into that. So this would look something like this, where now we have 0, 1, 2. So remember before we had origin 1, origin 2, origin 3. That's essentially, we can transform it, in this case, 0, 1, 2, which in this case probably doesn't really change much in our data. But you can kind of imagine if, like, we didn't have just 1, 2, 3, we could have something like 8, 6, 4, 5, 3, or whatever. It'd be the same idea. Okay. Does that make sense to people? Thumbs up that. Cool. All right, cool. So this is fine, but we still have that problem, like Chuck had mentioned, like 0, 1, 2. It still kind of makes it imply as if like one is better than the other, right? Or twice as good or something like that. So a typical way we do this is something called dummy variables. And also something that's called one-hot encoding. And so what this does, it takes, for example, let's say 1, 3, and 2 are the different labels for origin. And basically what it does here, it creates from one column, which the column is origin, where the value could be 1, 2, or 3. And it converts it into saying, okay, origin 1 has its own column, origin 2 is its own column, origin 3 is its own column. And what that does basically is just says, all right, now the value can only be 0 or 1, basically relating to saying, hey, is it origin 1, yes or no? 1 meaning yes, 0 meaning no, and does that for each one. So you actually see is that every line will only have 1, 1, 1, and the rest are 0. So this is kind of a nice way, because what ends up happening now is basically creating a new feature on its own, which is nice because now we can say, is it origin 1? Is it origin 2? Is it origin 3? And you can kind of imagine, like, what does that mean when you actually do the linear regression on here? Essentially what it does is basically turning on and off this factor. So I'm going to kind of jump ahead a little bit to like what this would look like. So imagine, and I know, well, let me see. I can try annotating. It hasn't worked every time I've tried it out with you all, but let's see if I can actually draw. You guys see my drawing at all? No, exactly. Stinking Zoom today. All right. So I'm just going to write it out. So like, if you imagine if we had like y equals, let's just call it like beta 0 plus beta 1 times, and we'll just call this x. So x is the origin, like that feature origin. What we transform this into is y equals beta 0 plus beta, I'm just going to call it like something else. So I'm going to call it, I don't know, beta 1, 0. So let's say 10 times x1 plus beta 11 times x2 plus beta 12 times x3. Oops, like this. So essentially what we did, we split this out into 3 different values. But the thing is that x1, x2, and x3 can only be 0 and 1. And if, let's say, one of these are 1, the rest are 0. So let's say, for example, say x1 equals 1. What does that look like? Well, that would look like y equals beta 0 plus beta 1, 0 plus, and then the rest are all zeros, right? So we have a bunch of other stuff. So I should add like maybe a little extra on the side here, is that maybe there's some other features like, x100 times beta 100. So there's some other features and stuff like this on the side here. Is that basically what this becomes is it's just a value here, a new constant plus the other features, okay? And so if I do this for x2, or sorry, x2 equals 1, well, that's just going to be y equals beta 0 plus beta 1, 1, plus the rest of these are all zeros, right? So this will be 0, and this will be 0. Does that make sense to people? Give me a thumbs up if that made sense. Sideways or I don't know. Okay, see a couple sideways, that's okay. I'm trying to think of the best way I can like write this out without having to be super complicated. But let's see if I can maybe make it like this. I don't know if this will help. I don't know if that's any clear.
Encoding is not right.
I'm sorry?
Is it a one-hot encoding? are you doing?
That's exactly what this is. So one hot encoding dummy
Oh.
and variables is exactly the same thing, if you're familiar with that terminology. So what I'm saying here is that if x1 equals 1, then that means x2 has to be 0 and x3 has to be 0, which effectively only keeps this part of the equation left over, and then these parts are removed. Does that make sense?
I think I missed something. Why do the other two have to be 0 if x1 is 1?
Good question. So good. The reason why that happens is because we define like x as being like the origin, and when we created x1, x2, x3, it's actually using this dummy variables or one hot encoding, where each one can only be 1 or 0, and then if one of these, because they're all connected together, if one of these are 1, then the rest have to be 0. So the idea is like it can only have one origin, right? It can either be origin 1, or it can be origin 2, or it can be origin 3, but not origin 1 and origin 2. So we always will have a 1, 0, 0, or a 0, 1, 0, or in this case, there's no example here, but 0, 0, 1. So they're all connected in that way. Does that make sense? Okay, cool. See a thumbs up. I saw a couple of nods, I think, afterwards too. So once you accept, like, okay, beta or x1, x2, and x3 have to be, only one of them can be 1 and the rest are 0. Essentially what that does is if x1 equals 1, you just add this extra term to the constant. If x2 is 1, it adds this extra term to the constant. And then if x3 is 1, it adds, in this case, beta 12 to this constant, plus what other features there are. So you can kind of imagine, like, what does that mean, like, effectively? Like, what does that look like? This is where I wish I could draw my screen right now, but so I'm gonna use my hand instead. But you can imagine, like, if this is the linear regression, like for, let's say, some feature, let's call it the weight. So this is the weight on the x-axis, and then y is the miles per gallon, is that when it's origin 1, it might bump it up. The constants of the y constant or the y-intercept down here, it kind of bumps it up by a little bit. So it moves like kind of the whole graph upwards. And then maybe, x2, so origin 2, maybe that beta that's associated with x2 is negative. So it's going to actually drop it down a little bit. It's going to subtract off that value. So essentially what your categories do is essentially move your graph up and down by a certain amount, kind of like changes the baseline, which is what that beta, that very first constant is doing. It's just changing the baseline. Okay, does that make sense?
So,
oh, yeah,
the purpose of this is like when we were talking about how certain categories might have different y-intercepts, like the cylinders. So it's kind of allowing you to move that around based on a category. That's
right. Yeah. So that's the way I think that's a great way to think about it, is that you can kind of think of like when you create categories, you're really just changing what the y-intercept's going to be. Yeah, cool. All right. Any other questions? I hope that kind of is a little clear. I wish I could draw because I think that makes it a little bit easier, but hopefully this makes sense. Okay. Cool. All right.
And Victor, that's because the categorical variables don't have any slope, like a continuous variable, essentially.
Right. Yeah. The slope, I mean, in some ways it kind of does have a slope, like this beta 1, 0 times x1. But since x1 can only be 1 and can only be either 1 or 0, it essentially just makes it go up or down, right? So yeah. So you can kind of think of it like not really having a slope. In some ways, you can kind of think of like all the categorical variables are all kind of like grouped together essentially as like, how do we change the y-intercept? And then there's all the other features that can change continuously. That's of course, if you do one hot encoding dummy variables, like they're the same thing, which is probably what you'll do if it's a category. So yeah, cool. All right, does that all make sense to everyone? Okay, I know that's a tough one to get your mind bent around. So if it does come up again, feel free to bring it up. So, can you explain that thing later on again, like after maybe digesting it over a day or two? So there's one thing that I kind of left out, and it's a subtle one, is that if 1, 2, and 3, these different categories that we created, these dummy variables, one hot encoding, if they're always tied together, let's say for instance, I don't know what 3 is, but I see the first one's 0, the second one's 1. What does 3 have to be? 0, right? Yeah. And if I saw 0, 0, 3 would have to be 1, right? So the thing is that this 3 feature, right, is kind of giving like the same information. It's redundant. And so what we'll typically do is we'll actually drop out that last dummy variable. And because basically the reason why we drop it out is because we're basically repeating ourselves. And why might that be a bad idea for just repeating ourselves?
For large data sets or something, just really inefficient for like millions of entries or something.
Yeah, so one could just be like, if you had many, many categories, right, you have a bunch of redundant variables, right? So that's kind of one reason. It's actually that's the secondary reason, is that there's just getting too many variables. Related to that though, would be like adjusted R squared, right? It's like, remember how we talked about like, we want to reduce the number of features if we can, right? So that's kind of related. There's also one other reason why.
There's
Linear.
a pattern.
I'm sorry, two people started talking, so I wasn't sure.
Okay, so because we can kind of tell what the third one is based on the first two, there's a pattern in there already. And when you're trying to come up with a formula for everything, that having that extra pattern in there is just going to muddy things up.
Yeah, that's kind of close to what's going on. It does muddy it up. And it actually is a very specific pattern. What it is that you're double counting. Is that essentially you might end up putting, you're basically saying like, let's say 1 and 2 together and 3 count for the same kind of like contribution, which does some weird things, what we call multicollinearity. And in multicollinearity, basically it's like these two features are really explaining the same exact thing. And so it basically double counts it, which means that it can actually make the features look more important than it actually is. Or what it can also do is it can kind of like siphon away the effect onto one of the coefficients for that. And it ends up doing this weird thing where it's harder to interpret. So what we'll typically do is actually get rid of one of these dummy variables. And what that effectively does is that you either, let's say if we have 1, 2, and 3, we drop the 3 one here. If we have 1, and that's like a value of 1, it's like, oh, it's origin 1. We add that to the constant. If 2 is 1, hopefully it's not too confusing, but origin 2 is 1, that adds a different kind of constant, right, to the y-intercept. And then if it's 3, we just don't do anything. It's 0, 0, which basically means is that 3 is kind of combined into the overall y-intercept. So you can kind of think as being like, usually you like to drop the value that is like the default value, or at least what you consider the default value for that situation. So if you kind of imagine, like if you had, let's say car color, I think it's a little more tangible for most people. If you had car color as one of these features, we had red, green, and blue, that's a weird colors for cars, but red, green, and blue, and black, right? And you had like, 4 different features. You might drop the black one because maybe black is standard. And so you can kind of think like, well, if it's not red, if it's not green, it's not blue, it's black automatically, which is put into the y-intercept. Okay, does that make sense to you? Okay, cool. All right, thumbs up if that made sense. Thumbs down, you're like, I'm like lost. Okay, I saw some thumbs up go sideways. Yeah, it is kind of tricky. But I would say is that what you can think about is that that category again is just kind of adding to the y-intercept depending what category it is. And the reason why we dropped that, one of the variables in there is to avoid what we call multicollinearity, which can get some weird interpretation effects. And so that default value becomes part of the main y-intercept. Okay.
I think I understand this is, you remember in our last project that we were creating those genre type into different columns and assigning each genre wherever that genre has, and the rest of the genre would get a 0. I'm kind of understanding this thing in a similar way that we created those tables, right?
Yeah, absolutely. I think it's very similar. In that case, there's a little difference just because I think we had 3 genres per category, so you could have 3 different ones. But if it was only one genre, it would be the same idea, where we have each genre, and then you'd have like just one if it was in that genre. So yeah, cool. All right. again, this is probably like the toughest, I think this is probably one of the toughest things to understand with multiple linear regression is figuring out like this categories with dummy variables. But in short, we'll have some more practice with this too. But I think it kind of helps a little bit think just like you're just basically just adjusting that y-intercept. Okay.
I have a quick question.
Mhm.
So does that mean like if we're already including 3, like let's say 3 moves the y-intercept up by 2 and category 2 moves it up by 3,
Mhm.
does that mean it's just always sitting at 2, and then if category 2 has 1, it moves up by 1? Sorry, that was a lot of similar.
I know it's hard with the categories. Maybe say A, B, and C. So category A,
Okay,
category B.
right, yeah. So if C moves it up by 5, but B moves it up by 6, we're always sitting at 5, and then when B is a 1, we move it up by 1 to get to 6.
Right. Okay. And this is assuming you drop that C column, right?
Right.
Yeah, that's right. So that C part is incorporated into the default y-intercept constant.
Okay. Yeah, I get it. Thanks.
Cool. No problem. Yeah, good question. Yeah, I know this is kind of tough to wrap your head around, and I do think this is probably the toughest thing. But I will say is that like it's better than me just saying this is what you're supposed to do, just drop 1. But that's kind of essentially what you do. In fact, if you look at this get dummies, you can see, I believe there's a parameter in here, drop first. You can actually specify drop the first parameter. So if I do this, for example, and it does drop first instead of the last one, because the idea is the first category is the default value. So that would incorporate into that y-intercept. Okay, cool. All right, cool. Let's move on then to the next part. What is my next part? All right. Wanted to make sure we got through these things that we wanted to. We talked about scaling. All right. So I'm kind of jumping a little bit ahead, so I'm kind of thinking these things. So we're going to talk about improving linear regression probably next time. I think that's going to be best. I did want to talk a little bit about model validation, but we talked about most of this already. So the one thing I talked about was like we have our train and our test sets, and I even mentioned a little bit of the dev validation sets. This is actually going to be something we're going to end up practicing a little bit. I'll talk to you guys at the end of the study group today. But we talked about saying, we want to make sure we have a training set that we use to basically teacher model, trainer model, fitter model to make sure it knows that data. And then we want to have some other data set that it's not seen before to really evaluate how well does it do? How well does it generalize to new data that's never seen before? So the solution is actually really easy to do with Sklearn. So, and first of all, I'm just getting this data right here. In this case, I'm just showing you, I'll just show you a little bit quickly. X in this case is with the features. So in this case, there's like 1, 2, 3, I don't know how many features actually. There you go. 8 features. So there's 8 features on here, and then we have the target Y, and you can see there's only 1. That's why there's no number here, and just 1,000 different points. Okay, so we have our data set. Okay, and if we look at this real quickly, if you're plotting it, we can look at these combinations of it, and we can look at this kind of like pattern within it. Taking a while for it to load up. See this I'm talking about? If you have too many features, it can even take even longer. So you can see like we have different patterns and stuff like this. You can see what the names are and all that stuff. And note these are just the features, not the actual like features in targets like we had before. So we can see different patterns in here. And the thing is that we want to capture enough of these examples. We're not giving it every single example. So what we can do is we can basically split this up. So this is a nice little, I wrote this little function in here. It's not really that impressive. The important part that you really want to care about is this guy right here. And what this is doing is basically doing this train test split. Now this train test split is actually in scikit-learn. So from sklearn.model selection, import train test split. And that allows us to basically specify, all right, here's the data set that we want to split. Here's the labels associated with those features. So note that the features in the target, right? That's what these two parts are. And so we're going to basically split that and create two different groups. Basically, we have the trained group, which is X train, Y train. And the reason we have X and Y is X is the features, Y is the targets, and that's going to be essentially our one group right here. Okay, and then we also have our X tests and our Y tests, which is going to be our test group. Okay, where we have our features and our target for that test group. Okay, everyone follow me so far? Okay, cool. And the way we specify this, we can specify saying the test size being 20%. So the test size will be 20% of the values, and therefore the train set will be 80% of those values. Okay, and note in this case, I put shuffle equals true. And usually you do want to shuffle it because that way you don't get like, if the values are all like in order, you don't get like 80% of like very low values, and then like the last 20% are like the higher values because it was ordered in some way. So usually shuffling is a good idea. If you do this as well, you should ideally put a random state. And the reason why you want to put a random state is basically to say, don't keep reshuffling it and retraining every time, because now you're just training essentially on randomness, which can do some weird stuff where you think you have a good result when it turns out it's just by pure chance. Okay, does that make sense? Give me a thumbs up. Any questions on what this function is doing? Okay, cool. So that's really what this function is doing. I just wrote a little function here. Basically, what I'm doing in this case is actually I'm doing different splits. So I'm doing this 10 different times with 10 different ways of doing it. And that's why I got rid of this random state here, is because I wanted to shuffle it and split it in 10 different ways. So that's what I'm doing here. Oops, did not run something. Oh, is it? There we go. Okay. So now what I'm showing you here, and you're like, what's going on here? These are the different splits that randomly selected it, and I'm actually plotting out the test values. So you can see here is that this all came, each of these came from the overall test set, or not the test set, the original data set, and I split it up, but I split up different parts. So the thing is right here, you can see this values seem to be relatively like along this line, but in this case, on this diagram, this split here, you can see I got some extreme values, which is a good thing. I do want this example in here. So the thing about this is that because you do want to have a train data, but also test data, by its nature, the fact that you're separating it out, you're not going to have all instances, right, to test on. You're going to sometimes get some of these extreme values in your test set or your train set, but other times by random chance, you might not. Okay, does that make sense to people? So that's actually an issue, right? It's kind of like you want to be able to separate these train and test, being, basically do your good, like practice tests and your final tests. But you might have some instances that aren't, that would actually be valuable in training or testing. So what can we do? Well, this is where cross-validation comes in, and specifically what we call k-fold cross-validation, which sounds super fancy, but basically what it's doing, and this is where maybe it bends the mind just a little bit. But this k-fold basically says we're going to split up the data. So we have k number of folds. So in this right here actually comes from Sklearn's documentation. You can imagine that we have some data separated that we're never going to touch until the very, very end. Okay. And then we have our training data. So this is the data that we actually are going to train our model with. And what we're going to do, we're going to take this training data and split it up into 5 different folds. So we say, okay, here's the first, 20%, here's the next 20%, and so on, right? So then it's evenly distributed. And then what we do, you can see how there's green right here, and then the rest is blue. We basically say, okay, the first fold, the first 20% of this data that we already partitioned, this is going to be kind of like our little, what we call our validation set. So it's kind of like our little internal test for us. And we train the model on everything else, in this case, all the green stuff. So you take all the green stuff, feed it into the model, and then you say, how well did it perform? And you test it on this little fold here, okay? And then that way you can get an idea of how well this model performed. Now, like we said, there's an issue that maybe this fold right here contains or doesn't contain some of the data that we would have liked to test on, right? So what we do, we actually do this second split and do the same thing again, but in this case, using this segment, the second 20% of data, right, as our kind of like little practice test, and we retrain the model with all this green stuff, okay? And then we see how well it does. So we basically do that, in this case, 5 different times. Okay. So everyone follow me on that?
And are you changing the model in between each of these iterations?
Yeah, good question. So in this case, it would be the same like initial kind of like setup, but we would find different, for linear regression, we would find different coefficients. The coefficients would be slightly different every time we trained it on this green stuff. And then the coefficients would be slightly different when we have this green stuff. And then that also means that the R-squared or other scoring metric will be slightly different from each other. Hopefully only slightly, but they could be very different from each other. Does that make sense?
Yeah, so by question, sorry, by the time you run all 5 folds or whatever, do you end up with some sort of like combined result for like, this is like the actual coefficients having gone through this many like training sessions or whatever?
Yeah, good question, because we actually build up 5 different models. And so you're like, okay, like we build all these 5 models, what do we do with those 5 models? You actually, afterwards, it's gonna sound weird, you actually ignore all that and then just retrain everything with all of the training models. So all 5 folds with no, like what we call like a little holdout validation set. And the reasoning is that we still want to use as much training data as possible. We want to have all those examples in there. So we actually will still retrain the whole model with all of the training data. And then, so the question is like, wait, then what was the point of that? Why didn't we just do this one first? The reason why we do these folds first is to basically validate saying, hey, is our method relatively good? Like, if the method of us building up this model, is it relatively good? And is it not going to be reliant on just what random data points we feed our model? So the idea is like, if we have very similar results for the let's say the scoring metric, like R-squared, if R-squared is relatively close to each other, each time we train the models, we're pretty confident then is that there's not too much variation depending on what data we feed it. So we can feel confident if we feed the whole data set now, the whole training data set, we can actually say, okay, we feel confident that we're not going to, we're going to generalize well enough to data that's not seen before. Does that make sense, Eric? Give me a thumbs up.
Yeah, perfect, thank you.
Okay, all right, and then I know, Becky, I think you had a question too.
Yeah, my question was the same actually.
Okay, good. So hopefully that makes sense then. Like, I think that is kind of a subtle thing that when you actually perform this, people say like, what did I just do? And basically you're using this to figure out, hey, did it actually like, did my model figure out, a good way to generalize? And what if you found, for example, let's say R-squared of like, 0.7, 0.72, 0.69, 0.68, and then you have like 0.8. You're like, whoa, like what just happened there? And it's like, it might just be dependent on like what you just tested it on. In that case, you might want to adjust your model to generalize better. So to generalize better usually means less complexity. If your R-squared value is all over the place, you want less complexity. And then let's say, for example, you're like, okay, got down less complexity, like, but I want to make a better model. You would increase that complexity, maybe add some new features, add some new, fanciness to your model, and then do this fold again. And you might get better R-squared values, but you hope that the R-squared values are relatively close together. The variance between each of those R-squared values is relatively small. Okay, cool. This does rely on the fact that the test data, which again, we never touched yet, it does rely on the fact that the test data is similar to the training data. So know that, for example, if you train your model on data that is like from 5 years ago, and then you test it on data that is, recent, like you might have different results. So it's important to know that you want to make sure your training data is as close as possible to what you actually are going to test it on, which your test data should hopefully be similar to what you eventually want to use it on when you deploy the data. Does that make sense, people? Okay.
Yes. One quick question. If you could scroll up a little bit to the function that you had made. So for this set, you did 10 splits, right? And so in the diagram down there, like it would be 10 different rows, but because it's 20%, keep going.
Right, keep going.
Keep going down.
Okay. So
you know how it's like split 1, split 2, split 3, split 4, split 5. That would happen 10 times for that.
Yeah, if this model doesn't actually do that, but like that would be the idea. Like if you had 10 different splits, you could have like 10 different folds. So
Okay.
yeah. And this is where it typically is like, okay, how many folds should I do? The extreme version of this is that you basically make one data point as your test, and then you train on everything else. It turns out that's actually not super good at performance. Usually the typical number is around 8. I think if I remember this, like I think research shows about 5 to 8 or 5 or 8 folds for whatever reason tends to actually do pretty well. So usually you'll see it if I show you a little bit like what that looks like when you actually do a cross-fold validation. Sorry, it's showing you a whole bunch of stuff. That's why I'm kind of like looking for the right stuff I want to show off. Maybe this is not a good place to check this out. I'm trying to remember the documentation of where this would be. And so there's different ways you can do this, but I won't go through this any further. But typically, I think research shows is that it typically is about 5 folds or 8 folds do really well. The extreme fold of this would be like n fold, where you like take literally however many data points you have and fold it that many times and then retrain it. And it turns out that just doesn't really do a great job. So yeah.
So this would be a technique that you can use on any type of model, not just multiple regression.
That's right.
Okay.
Yeah. So this is why like we usually kind of save this a little bit more to phase 3. But I think it's important enough to show now about for, when you're doing linear regression. So I talked about the model, very generally. And so those parameters for linear regression, it's going to be coefficients that are found. But for other models, there'll be different kind of parameters that define that model.
And when you say, do you typically use this? Is this like a standard that you do pretty much every time?
Yeah, so this is kind of like that validation part. So I mentioned about that validation test set. You can think of this fold 1, the blue folds here. Those are kind of like little dev validation test, or sorry, sets, right? Your validation dev sets for that specific model. So you're basically validating and saying, hey, does this model actually, train well? And then you're like, okay, it looks like in general, this will work really well. So I can train the whole thing over and encompass all of the data that I possibly can train, and then do a final test right here. Yeah, so I think this is where, let's see here. Okay, good, we have about like 13 minutes left. So this is where I get to tell you all like how we're gonna practice this a little bit. So I'm gonna kind of go over this a little bit more tomorrow, but I wanted to give you guys a head start, is that we're going to have a little Kaggle competition. And the fun thing is going to be, is actually you guys are going to be competing with each other as a class. So you don't have to worry about, like competing about some random people or whatever. So I'm still building this up to make sure, we have data. But I wanted to walk you guys through a little bit Kaggle and actually show you how we can, how you would do this. Okay. So let me go ahead and open up Kaggle here. Okay. So first of all, real quick, thumbs up if anyone has signed up a Kaggle account. Okay, I see a couple thumbs up. Cool, awesome. So the first step is before tomorrow, make a new Kaggle account. So that's kind of like the first step. And what we're going to do, we're going to have a competition. So I'll show you actually one of the competitions I had with another cohort that will be very similar to this. So this was a practice again for they did linear regression in this case. And what this is basically, if you've ever seen a Kaggle competition, I'll show you exactly how you guys get this. Basically, you're provided with data. So in this case, we have our test set and our train set. And so in this case, I believe this was like predicting, I think it was Airbnb. So I think it was predicting the price of an Airbnb listing based on the features given. Okay. And so what you'll get is 2 different files, a train file, .csv in this case, and a test file. And for this competition and for most competitions on Kaggle that are like this, the train file will contain all the features, and then let's see if I can kind of scroll over, all the features, plus usually at the end here, maybe it's not on here. I'm trying to remember if this was the right target that I'm thinking of. I'm typing train, right? Sorry. So anyway, the train file should have all the features plus the target at the end. Okay. So if I look at, maybe it wasn't the price of the thing. Maybe it was, sorry, I misspoke. It's supposed to be, I think, the review rating. I'm trying to remember exactly. Oops. Let's do compact. So I'm trying to remember off the top of my head. Maybe it's not, oh, that's why I can say, oh, it was the price. Okay. So in this case, in this data, in this category competition, we had the training data, which was all of these categories, all of these features. So we had the ID, the host ID, host name, longitude, latitude, room type, minimum number of nights, I think, and so on. And price was the target you're supposed to predict. So your train file will have all the features plus the target. Your test file will have all of the features. There might be some missing values and stuff, but each of those columns, but no target at the end here. Okay. And the reason why is because what you'll do is you'll use the training file to build up a model by basically iteratively trying to find the best, scoring metrics that they R-squared. So you try to get a good R-squared by using the target at the end to see how well your model does. And then once you feel confident that your model is, a good, robust model that will generalize well and that will do a good job predicting, you take your model that you already trained and feed in the features on the test data. And that's going to predict a target. So in this case, it would predict the price. And so that price value now, we have, in this case, would be like the ID would represent each data point. You would have essentially, your submission would be your ID of the data point in the test file, and then your predicted target value for that test file. Okay, everyone follow me so far? Okay, so again, that target is going to be predicted by however you define, however you make your model. When you have that, you can submit that submission now and say like, hey, this is what my predictions were for these features for this data point. And what that's going to do, it's going to load onto the leaderboard to see how well you performed. And in this case, I think the scoring was the root mean squared error. So basically how far away these points are. And the idea here is that you want to, ideally, on the public leaderboard, to get as good as you can. So you can see here, we actually had different teams here. We can actually talk about if we want to do teams or individuals or whatnot. But you can see here, we have a few people who are a few teams that scored this way. And you can see they can actually do this multiple times. So you can actually keep submitting new entries and seeing looks like, Team Talon, doing a better job. Maybe I can need to reevaluate how I'm doing my model, do that. So the reason why I like doing this is because it's a good practice, because I'm giving you data, right? I'm giving you this data, this training set, and then you're going to have to make a prediction off this test set. And then we're going to see how well you perform. Now, there's a subtlety here, is that you want to be careful about overfitting, because what happens is that what will tend to happen here is that people will kind of reiterate, kind of change up their model, make little tweaks and stuff like that, and getting better and better R-scored, and then kind of getting this result back. You don't know what exactly you did wrong or did well on. You just know what your results are backwards, right? So it's kind of like, oh, you submit your predictions for tests, and basically you just get a number saying, hey, you did this well, but you don't know which ones you got right or wrong. Okay. Well, the thing is, we have something called the public leaderboard, and the private leaderboard won't be available until the very end. So until the competition finishes. And what that is because basically there's a portion of the test file, some portion of that, in this case, I think it's 80%, 80% of the test data will be kept, so it'll show you that you're a score, but 20% of the data, it never checks how well you did. It's the same 20% every single time. So you never actually know what that final score is going to be. And then when the competition's done, we save your model in there, or we save your results. And then we say, okay, how well did you do on this 20% that you've never seen before? And so it's kind of interesting. And I think this is why I like doing this kind of like little activity, is that you'll tend to see that people will tend to start overfitting on this public leaderboard data. And the other 20% that you never see, you don't perform as well on it because you've been kind of tuning your model to perform better and better on this public leaderboard. So if you look closely here, and see if I can do this. If I look at public board, I think Jam and then Team Talon were the two top teams. You can see here in this case, Team Talon actually ended up doing better in the long run. And it ended up being is that Jam, in this case, it looks like Jam might have started overfitting on the public data, even though they had the best score initially. when we actually see the final private score that they didn't see until the competition is already done, they've made all their submissions, you actually see that Jam actually did not do as well, and Team Talent actually did better. And you can kind of see this a little bit in the entry levels too, is that they did 8 entries. So they were doing 8 different models. So it's possible that maybe they started overfitting on this data, stuff like this. And I think it's a good practice because it kind of like, one is like actually making a decent model, but the other part of it is also knowing like how to make sure you don't overfit your model. So I think it's a good practice. And this relates really closely to our actual project that we'll introduce at the end of this week. Okay. Sound pretty good? Any questions about that kind of like overall structure? We'll go into more detail. I think we'll actually spend some time tomorrow actually like showing you how to make a submission and all that stuff.
So this competition, like when do we have to finish? Like, is it before the project?
So I don't want to stress you guys out to think of like, oh, I have this competition and the project as well, even though I think it's a little bit more fun. But I don't want you to think about like the competition and then also the project. So I'm going to actually end this on like, I think either on like Friday night of this week. So like, you know, just a couple of times you can do it, or we can actually finish it on Sunday. So when we maybe start project week, it's next week, Monday, we can actually say, okay, we'll finish the competition on Sunday, and then we can kind of come back together on Monday and kind of discuss it. I'll kind of think about that, you know, what you all think. And then also consider if you guys would like teams or if you would just want to do solo. I think the team might actually be a really beneficial part of it. But if you want to be solo, you definitely could. Okay. Cool. Any other questions?
More importantly, what are we winning?
Fame and glory, right? No,
worth it.
$1 million.
Yeah, if someone wants to chip in for $1 million, I'll compete with you all too. But yeah, no. For the record, competitions in Kaggle, you can actually win real money. This obviously is more of an in-class competition, just for fun. So you'll have bragging rights. Is probably the biggest thing you'll have. Also, you'll have good practice for the actual project. So there's that too. Let's see here. Okay. Any other questions before I kind of wrap the last part up? Okay, so you have homework. This is your homework. It's really easy. So just to get you guys started and get used to Kaggle, what you need to do is make an account, and I'll share this on Slack, is make sure that, for example, when you first create a Kaggle account, you are a novice. But to be really taken seriously on Kaggle, but really just to get you guys like, okay, like get familiar with it, is I want you to complete these things, at least as many as you can. Ideally is what I really want you to look at are these like run a script, make one competition, task or submission, make a comment. I'll send this link in here and I'll basically it'll checkbox each part. And then what you'll see on your profile is you'll see like this little icon. It'll start with green, but once you do those, like if you do all of those things, you actually see that you'll turn blue in that case. And basically that just allows you to actually have real, like basically Kaggle kind of treats you as like, oh, you actually are participating on this thing. You're not just someone who just randomly did this once and then do it. If you really don't want to, it's not a big deal. But I think it's a good kind of practice to kind of get an idea of how Kaggle works. If you basically majority of these tasks, I think that'd be get you familiar with how this works. Okay, so I'll send it on the Slack. That is your homework for today or tonight. So tomorrow we'll actually introduce the Kaggle project competition, and we'll work on that together.
And Victor, would the project that you're putting out there, would that count as that make one competition?
Yeah.
Okay.
I believe so. I don't think it wouldn't, but I believe that would count as one of the make a submission. So yeah, cool. All right, everyone. Well, with that then, hopefully you guys feel a little excited about, you know, this competition coming up and everything. We'll walk it together. I'll show you all how to do like an example, like building from scratch, getting the data, building a linear regression model, and then submitting that that submission submitting that submission to Kaggle. Okay.
Can you send the link to that Kaggle dataset, Kaggle link, you know, today, or we have to wait tomorrow?
Oh yeah, I don't have the competition up right now, but I can share you guys maybe this competition. I think this is not, let me just double check that I can actually access this. Okay, yeah, I'll send you an example of what that competition looks like right here. It'll look similar to something like this.
Oh, it's going to be a brand new competition.
Brand new competition, yeah. I'm gonna try. For the record, you probably, like, if you really wanted to, you could probably cheat, but try not to cheat, right? It's more for your education and stuff. No one's winning $1 million. For the record, though, there are people who have cheated on real Kaggle competitions, and not great things have happened to them because it kind of made them a little blackballed in the data science community. So, yeah. Basically, don't try to cheat unless you find an interesting way to cheat and then share it with the world. Say, this is how I would cheat, but I'm not going to. Anyway, that happens too. All right, everyone. I do have to go to another meeting, but I'll share these links on Slack, and I'll see you all tomorrow. Take care.
Thank you.